Hi all, let's see the next topic of input output organization, which is interrupt initiated IO. In today's lecture, we are going to discuss about an introduction to interrupt initiated IO and what is a priority interrupt and what are the types of priority interrupts. And coming to the types, we discuss about the software interrupts and hardware interrupts. Coming to the introduction of interrupt initiated IO. In the previous lecture, we have already discussed about a programmed IO. So, in case of a programmed IO, the main disadvantage of programmed IO is that the computer or the CPU of a particular computer has to keep on checking the flag bits of the corresponding interface unit in order to determine if there is any data that has to be transferred from the interface unit of the corresponding device to the memory unit of the computer. So it requires a CPU intervention, and CPU has to keep on continuously checking the flag bits going into a loop. So it is so here the CPU is wasting its time checking the flag bits rather than executing the other programs. So in order to overcome the disadvantage of a programmed IO, we come up with the interrupt initiated IO. So in this type of an IO, the computer does not check the flag bits. The computer, in the sense here, the CPU does not check the flag bits. It continue to perform its task. And it is the responsibility of the interface unit to interrupt the CPU whenever it has a corresponding data in its register that has to be transferred to the memory unit of the computer. So whenever any device or interface unit of any device wants the attention of the CPU, the interface unit of that device sends the interrupt signal to the CPU. So here the CPU time is not being wasted because it is continue performing its task, and whenever a device input output device requires its attention, that will be intimated to the CPU by means of an interrupt signal. So in this method, an interrupt facility an interrupt command is used to inform the CPU about the start and the end of the transfer. In the meantime, the CPU will be executing the other program so that its time will not be wasted. So, whenever the interface unit of a device determines that the device is ready for the data transfer, it generates an interrupt request and send it to the CPU. So interrupt here means that it is a special signal that is generated and that requires the intervention of the CPU or CPU's attention. So whenever a CPU requires such a type of a signal, it temporarily stops the execution of the current program and it branches to the service program or interrupt service routine of the process that has initiated the IO transfer. So, if say for example, the printer has interrupted the CPU. At that point of time, the CPU will stop whatever program it is executing currently, and it will go and execute the interrupt service routine of the current uh, interrupt service routine of the printer, which interrupted the particular CPU. And after completing the interrupt service routine of the corresponding interrupt, it returns back to the task what it was originally performing. So that is how it deals with the interrupts. So the data transfer between the CPU and the input output devices will be intimated, initiated by the CPU. So for if say for example you have a computer which have different types of input output peripherals connected, at that point of time there are more and more number of IO devices attached to the computer, there is a possibility that at same point of time more than one device can generate an interrupt. So at that time when an interrupt is generated from more than one device which is requesting for the CPU intervention at the same point of time, then how which device has to be serviced first is determined by the CPU based on the priority interrupt system. So the priority interrupt system is used here to determine which device to be serviced first when there are multiple devices which generated the interrupt signals. So in this case of priority interrupt, the devices are given certain priorities based on their transfer speed. So the device with highest transfer speed is given a high priority, whereas the slow devices are given as lower priority. So for example, if you consider a magnetic disk, it is given as a high priority because the data transfer rate is very high compared to your low priority devices, slow devices such as your printer, monitor and all, they are giving a lower priority. Here, establishing the priorities can be done in two ways. In case of an interrupt initiated IO, one is using a software approach and other is a hardware approach. So in software approach, we have a mechanism called polling mechanism, which is a software based approach. Whereas a hardware approach, we have a daisy chaining mechanism and parallel priority interrupts or parallel priority encoder. So software approach is basically done with the help of a program, software program. The mechanism is implemented. By in case of a hardware approach, it is done with the help of a hardware. So let's see each one in detail. The first type of a approach, which is a software priority is a polling mechanism. So here, each and every input output device which is connected to your system is given a priority based on the transfer rate. So if you consider the priorities 0, 1, 2, 3, the lowest number is given as the highest priority, whereas the highest number is given the lowest priority. So here this software approach is a software based approach which is used to check the priority of a certain device based on by using a program. So a program is used here to check if the high priority uh, program or a high priority device has given the interrupt signal or not. So if high priority has generated the interrupt signal, then the CPU will execute the interrupt service routine of that particular device. If not, if that is not the device which is having the highest priority, it will check for the next high priority device. So if you consider 0, 1, 2 and 3, say for example device 0, say it might be a printer. It has generated an interrupt request to the CPU. In that case, the CPU, since this is the highest priority 0, the CPU will execute the interrupt service routine of the program. Say for example, a device 1 and 2, both of them has generated the interrupt to the CPU at the same point of time. In that case, since device 1 is having a higher priority than device 2, the CPU will execute the interrupt service routine of the device 1 and not 2, because that is the next high priority device after device 1. So since 1 is a high priority device among the both, the interrupt service routine of device 1 will be executed first by the CPU. So where does this interrupt service routine program of the corresponding device is stored in your is being accessed by the CPU. So whenever a CPU receives an interrupt request, it has to execute the interrupt service routine of that corresponding device. But where can the CPU find that particular interrupt service routine? So there are two types of addresses. One is a vector address and another is a non-vector address. So for each and every device that is connected to the computer system, it has its own interrupt service routine program address. That is a certain location in the memory which is assigned for that particular device for storing the particular device interrupt service routine program. And for each and every device, this address is different. So we call it as a vector address of that particular device. And coming to a non-vector address, in some type of systems, all the interrupt service programs of all the devices will be stored at a fixed location in the memory. It will not be at different locations for each device. All the device interrupt service routines will be stored at a fixed location in a memory. We call it as a non-vector address. So the vector address of that particular device, the CPU is going to access the vector of the address of that particular device which has sent an interrupt signal to it in order to execute that particular interrupt service routine of the device. So coming to the disadvantage of this particular polling mechanism, the amount of time the CPU will take uh, to find out which device has generated the interrupt is more than the amount of time that the CPU takes to execute its interrupt service routine program. So, say for example, if there are more and more number of devices, input output peripherals connected to your system, obviously the amount of time say for example, if there are 20 devices, out of that there are 10 devices which have generated the interrupt at the same point of time. So the CPU will take more amount of time to find out of 10 which device is a high priority, then where is the interrupt service routine of that particular device. So it takes more amount of time in finding out this rather than executing the interrupt service routine of that particular device. So that is one of the major disadvantage of a polling mechanism. So next type of a mechanism is a hardware priority interrupts. So polling is a software-based approach. Coming to a hardware-based approach, so a hardware-based priority interrupt unit, it functions as an overall manager in the interrupt system environment. So what it does is it will accept the interrupt request from many sources or many devices, and then it determines out of the incoming requests which is having the high priority. Say a keyboard, a printer, and a magnetic disk. All the three has generated the interrupt request to the CPU at the same point of time. Then this hardware based approach, it will receive the interrupts from all the three devices at the same point of time, and then it will first understand which is the device which is having the highest priority out of these three, and then it will identify, and then that particular device interrupt request will be sent to the CPU. Only that device interrupt signal will be sent by the hardware unit to this particular CPU. Not all the interrupt requests will not be sent to the CPU. So to speed up the operation, each interrupt source has its own vector address in order to access its interrupt service routine. So here we doesn't require any polling mechanism because all the decision is established here by the hardware, which is a hardware priority interrupt unit. And the hardware priority function can be established either in a serial manner or a parallel connection. The serial connection we call it as a daisy chaining method, and the parallel connection is called as a parallel priority encoder. So in hardware we have two approaches. So this hardware priority, it can work either in a serial manner or a parallel manner. If it is working in a serial manner, we call it as a daisy chaining method, and in case of a parallel connection, we call it as a parallel priority encoder. So let us see the first approach in a serial manner, which is called as the daisy chaining priority. So the daisy chaining method of establishing the priority, it consists of several connections of all the devices that request an interrupt. So if you look at the daisy chaining method, so this is a daisy chaining priority method where we have multiple input output peripheral devices which are connected to the CPU in the system, and each devices are placed in the order according to the priority, which means if you take a magnetic disk which is a high priority device, that will be your device 1. Next high priority device, if it is a keyboard or a monitor, that will be device 2. Next device 3. So the devices are connected according to their priority. High priority devices are placed first, and the last will be your low priority device. So in that way they are connected to your CPU, so through this interrupt request line. And we also have two inputs for the two things, one input and one output for the CPU. One is the interrupt request line and other is an interrupt acknowledgement line, which is an output given from the CPU to the devices. So device 1 will have the highest priority, where device 3 will have the lowest priority. So here I am taking an example of only 3 devices connected to the system, and if device they are each and every device vector address. Device 1's vector address is called VAD1, device 2 vector address VAD2, and so on. All the vector addresses are connected to the CPU through the bus, data bus. So for example, how this is daisy chaining works is, if the device has generated an interrupt, the corresponding interrupt request line will be enabled. Say for example, the device 1 has want to interrupt the CPU. Say device 1 is a magnetic disk. It want to perform either a read operation or a write operation. So it needs an intervention of the CPU. So it will enable the interrupt request line. So whenever the CPU receives an interrupt request line, it will enable the interrupt acknowledgement line. So whenever device 1 receives an interrupt acknowledgement line, since this is a high priority device out of all the devices and it is the only device which has generated the interrupt request, it will place, and this interrupt acknowledgement line will be given as an input to a device 1 to through PI. There are two things here. One is an input to output. PI is a priority input and PO is a priority output. Through priority input, it receives an interrupt acknowledgement signal, and whenever it requests gets this signal from the CPU, it places its vector address onto the processor data bus, so which is sent to the CPU, so that the CPU will go to that particular address and execute the interrupt service routine of that particular device. Say for example, the there are two devices, device 2 and device 3, which want to interrupt the CPU at the same point of time. So both of them at the same time, they will generate an interrupt request. They will enable the interrupt request line of the particular CPU. So whenever CPU receives an interrupt request enable, it will send an interrupt acknowledgement signal. So which will first go through device 1's PI. So whenever it is received by device 1, since this is not the device which has generated an interrupt, it will just forward that particular acknowledgement to the next device through a PO, priority output. So it reaches the device 2. So now out of device 2 and device 3, the next high priority device is PI. So device 2. So the device 2 will place its vector address onto the processor data bus, and it will block the next acknowledgement line of the next device by placing a 0 onto the P naught. So whenever 0 is placed here, even though this device has requested for the interrupt from the CPU, whenever 0 is received, it means that it is being blocked because there is one more device which is being serviced by the CPU. So this vector address of device 2 will be sent onto the bus to the CPU, so that the CPU will access the vector address of device 2 interrupt service routine and execute it. Once it is done, then so this is how a daisy chaining priority works. So if any device want to interrupt the CPU, it generates an interrupt. The corresponding line will be enabled and the CPU responds to the interrupt by enabling the interrupt acknowledgement line. This signal is received by device 1 as its priority input. So this acknowledgement signal passes to the next device through P0 only if device 1 is not requesting an interrupt. If the device 1 has a pending interrupt, it blocks the acknowledgement signal to the next device by placing a 0 into the P0 output. So it then proceeds to insert its vector address onto the bus. A device that is requesting an interrupt has 1 on its PI will intercept the acknowledgement signal by placing a 0 on its P0. So if the device does not have a pending interrupts, it transmits the acknowledgement signal to the next device by placing 1 on its P0, so that the next device will access the interrupt signal, acknowledgement signal. Thus, the device with PI is equal to 1 and P0 is equal to 0 is nothing but it is having the highest priority, that is requesting an interrupt, and it places its VAD onto the data bus. So this is all about is a daisy chaining arrangement. This arrangement, it gives a high priority to the device that receives the interrupt acknowledgement. So whichever is the first high priority device, and since they are placed according to the priority, if it receives an interrupt acknowledgement, if it has interrupted the CPU, that will be serviced first by the CPU. So the farther the device is from the first position, the lower will be its priority. Coming to the disadvantage of a daisy chaining priority mechanism, this is same as a polling software approach where the time taken to find the device that generated the interrupt is greater than the execution time of an interrupt service routine program of that particular device. Because here we are taking only three devices, but if we consider a large system with more number of devices, obviously the time will be the time taken by the CPU will be more than, because it has to send an interrupt signal acknowledgement, enable the interrupt acknowledgement line. It has to go through all the input output devices, and then it has to find which is the high priority device. Then the vector address of that particular device has to be placed onto the bus and to be received by the CPU. All this, it takes a lot of amount of time. So that is one of the major disadvantage of a daisy chaining priority approach. So the next method of a hardware priority interrupt is in a parallel manner is a parallel priority interrupt, or we also call it as a parallel priority encoder. So if you look at the parallel priority interrupt or parallel priority encoder, we have two registers here, which is an interrupt register and a mask register. So for each and every input output device present in the system, an entry will be allocated in your interrupt register. So here we have four input output devices called disk, printer, reader and keyboard, which are given as numbering 0, 1, 2, 3. So And correspondingly, the mark register bits will also be allocated, entries will also be allocated for all the devices of your interrupt register. So 0 for disk, 1 for printer, 2 for reader, and 3 for keyboard. And initially, the all the entries of your mask register bits will be set to 1. All are ones. It can be either 0 or 1. So all are initially set to 1. Next, we have an AND gate. To an AND gate, we are connecting this particular interrupt register and a mask register bit. So consider disk is so this here also we are arranging so say for example the disk want to interrupt the CPU. Then this particular disk line will be set to 1. It will enable the interrupt by setting this line to 1. So when and the mask register bit is also initially 1. And these two are ones are given to this particular gate, the output will be a 1. Which means the priority encoder, what it does is, so the priority encoder is a circuit that implements a priority function. So when there are more number of interrupts coming from the particular multiple devices at the same point of time, it will identify which is a high priority device and that particular device will be given a priority. So since this is one and say all the three devices that doesn't generate an interrupt, so these outputs will be zero. So particular device's address will be placed onto the bus like that. Say for example, consider there are two devices which requested the interrupts to the CPU at the same point of time, printer and reader. So this line will be one where you get an I1 as one because this bit and this bit all are ones. So similarly for reader, also both the lines will be one. So here we get a one. So I1, I2 outputs will be one. So when you have I1, I2 as one, based on the truth table, if you see, so this is a truth table. So if you take I notes or based on the devices, I note, I1, I2, I3, I note is a high priority device and I3 is a low priority device. So when your interrupt request of I note, the priority encoder output of I note is 1, the remaining all are don't care conditions because this is a high priority device. And in the second case, if I naught is 0, there is no interrupt from I naught and there is an interrupt from I1, the remaining two are don't care conditions because this is a high priority out of these these two, but this is a high, but this is since this is 0, this is the next high priority device. This has to be serviced first by the CPU. Similarly, if there is no interrupt from I naught I1 but there is an interrupt from I2, this is a don't care condition. If there is no interrupt from I naught I1 I2 and if there is an interrupt from this low priority device I3, then this device will be serviced. And there is no interrupt signal from any device, nothing will be serviced. So here, if I naught there is an interrupt, the output of your bus will be 00. So device 0 means 00. In case of 1, 0, 1. 2, it is 1, 0. In case of 3, it is 1, 1, the output. Okay. So provided the interrupt status bit, it's set to 1. So when there is an interrupt from these two, when since I1 is a high priority device according to the truth table, this address of x and y, which is nothing but 0, 1. So 01 will be placed onto the bus. So whenever there is an interrupt from any one of the device, this interrupt IST will be set to 1 provided there is an interrupt enable should be 1. So whenever only when the interrupt enable is 1, the CPU will want to take the interrupts. So only when the IEN is 1, the CPU will take the interrupt from the devices. Whenever there is an interrupt from any of the devices, this IST will be 1, and when these two are given as an input to this particular AND gate, the 1 and 1, it becomes a 1, which means there is an interrupt to the CPU. So CPU will receive an interrupt. So when CPU receives an interrupt, it will send an acknowledgement. From the CPU, an acknowledgement will be enabled. That is given as an input to this AND gate along with IEN and IST. So all the three are ones, one, one, one. So it will be the output will be one. It will enable this bus buffer. So these particular devices I1, in this case I1. So the I1's VAD address will be sent to the CPU so that the CPU will access that VAD address and it will execute the interrupt service routine of that particular device. So when there are multiple requests from multiple devices at the same point of time, the priority encoder is a circuit that determines the priority of the device, and based on the priority, the particular device interrupt service routine will be done. So this concept is called as a parallel priority interrupt or a parallel priority encoder. So it consists of an interrupt register whose individual bits are set, the magnetic disk being a high speed device, higher priority, the printer the next priority, and so on. The mask register bits will, will be the same number of bits as the interrupt register, where all are zeros. Each interrupt bit and its corresponding mask register bit is applied to an AND gate to produce four inputs to the priority encoder. And the priority encoder generates 2 bits of vector address which is transferred to the CPU. So the priority interrupt is generating a 2-bit vector address. Another output from the encoder sets an interrupt status flip-flop IST when an interrupt occurs. So the interrupt enable flip-flop can be set or cleared by a program to provide the overall control of the interrupt system. So the outputs of IST and IEN provide a common interrupt signal for the CPU. So these two will provide an interrupt to the CPU. The output of IST and IND provide a common interrupt signal. The interrupt acknowledgement signal from the CPU enable the bus buffer in the output register, and a vector address will be placed onto the bus. Okay, so the priority encoder is here. It is a circuit that implements a priority function, and the logic is that if more inputs arise at the same time, so if more than one device generates a interrupt signal at the same point of time, this priority encoder decides which is a high priority among, say, for all the four generates an interrupt signal to the CPU at the same point of time, then the priority encoder decides which is a high priority among all the four, and that based on that particular device address will be placed on VAD address will be placed onto the bus. So this is how the parallel priority interrupt works. So this is all about interrupt initiated IO.